Hello, and welcome to the 73rd edition of Crossing Thin Ice, a podcast series about risk management for insurers. I'm Dave Ingram, and today, as always, I'm joined by Max Rudolph. We usually take food availability for granted, but today, Max is going to talk about how one of the practices that has created the abundance that we are used to could lead to serious problems in the future. That practice is monoculture farming. Some of the issues that Max will deal with go back to concerns expressed by Franklin and Malthus in the 1700s. Others are tied to scientific methods that are as advanced as rocket science, or maybe more so. We will also hear about three terms that are new to me at least: social fragmentation, continuum analysis, and drive to thrive. Listen carefully. I'll be back with a quiz at the end. Before we start, I do want to mention that nothing in today's podcast should be interpreted as investment advice, but it is sure to be educational and thought-provoking. Let's get started.
Defining the proper question to answer can be the hardest part of a problem. Is it more noble to save millions from starvation, only to have their descendants, with twice as many people, die a generation or two later? Is that even the right question to ask, given that technology continues to improve and new solutions may be just around the corner? Is this a global warming issue, with the Earth increasingly more fragile to extreme weather events, drought, and loss of biodiversity? We experienced such an initiative following the Great Depression and World War II, increasing food supply and reducing starvation risk. Norman Borlaug started with wheat in Mexico, increasing yields and developing a variety that was resistant to disease. Borlaug went on to win a Nobel Prize as the father of the Green Revolution, initially saving an estimated 1 billion people from starvation. Benjamin Franklin and Robert Malthus wrote essays in the 1700s, concerned that populations would grow faster than the ability to feed them. The core of Malthus's idea was that population grows geometrically and food arithmetically. He's likely right over long time horizons, but so far, numerous pivots to new sources of fertilizer have expanded food production. Natural population balances occur due to war, disease, and famine, and are often triggered by overcrowded conditions and resource scarcity. Reduced child mortality and increased education have incentivized smaller and delayed families. The high point of each population cycle comes when humans overconsume, leading to one of the automatic rebalancers to kick in. This leads to regional conflicts as resources become limited. This could play out today as global warming worsens and creates short supplies of fresh water and arable land. Biodiversity and economic inequality are also important to consider as they interact with limited resources. A reduced fertility rate has bought time for humanity to act, but longevity gains and forced migrations as regions become unlivable due to a changing climate will add to the challenge. At a high level, the primary concern is famine and increased mortality. Of secondary importance, but still important for financial institutions like insurers, is reduced market values for all assets as demand dries up. Mortality and asset returns are viewed as uncorrelated assumptions. If there are concentrated negative outcomes, this could create a solvency risk for some insurers and could interact with regulatorily identified fragility concerns about some asset valuations and become a systemic issue for the industry. This is a classic confrontation of focus and concentration against diversification. A single crop planted with a single seed and fertilizer combination and in a single location can generate high yields under favorable conditions. Risk management through diversification leads to lower peak yields, but fewer periods of famine when conditions deteriorate. There needs to be a balance. Many locations were experiencing poor yields during the Depression, and the poor economic conditions meant solutions needed to come with minimal funding. Stem rust, a form of wheat rust, was and is a problem that led to recurring crop failures in developed countries and famine throughout the emerging economies. Borlaug used his training as an agronomist to breed wheat resistant to wheat rust disease. A downside to the technique developed is that it requires a great deal of fertilizer, uses lots of pesticides to eradicate insects, and contributes to air pollution and greenhouse gases. Borlaug's supporters say he kept billions of poor people from food insecurity and death. His detractors say he postponed the inevitable and created a future ecocide. As a complex adaptive system, Earth's ecosystem can't linearly be reduced to a few levers to be manipulated and optimized. Interactions matter, and there are often unintended consequences. The critical path for plant growth is the nutrient least present in the soil, generally nitrogen. The need for fertilizer has led the world to pivot from human waste to bat guano to synthetic ammonia. Along with the ozone and climate change, unwanted waste nitrogen will keep scientists engaged until they can successfully manage issues tied to environmental and health problems. Rice was later added as a miracle crop by Borlaug, but irrigation and artificial fertilizer created unwanted side effects, including drained aquifers, aquatic dead zones, and social upheaval. Perennial crops that store carbon and don't require as much tilling of the soil will perhaps be a new pivot to help slow global warming, as could alternative sources of protein like insects. Getting fresh water to the right place to support crops and humans may be another. We should learn from humanity's mismanagement of what was once called the Fertile Crescent. There are a number of reasons why monoculture farming is undesirable. Repeated plantings of the same crop can lead to erosion and nutrient depletion, with a reduced ability to retain water. Crop concentration is vulnerable to pests and diseases. An over-reliance on pesticides, which kill pollinators, much of our agriculture depends on bees, and get in the water and soil while bacteria build up resistance. An enhanced likelihood of crop loss in any one year leads to higher food insecurity. Farming as a profession becomes more fragile with crop failures and loss of price and input cost stability. Interactions with the changing climate are also a negative, forcing a move to genetic modifications because the plants can't evolve and build defenses quickly enough. There's no easy fix. Geoengineering solutions inevitably lead to unintended consequences that also need to be addressed. Even if initially successful, they create an increasing cycle of actions that work until they don't. Even without experiencing tipping points that rapidly change the current environment, ongoing trends of increasing temperatures will lead to sea level rise, zoonotic diseases, freshwater shortages, regional conflicts, and weather pattern changes that alter agricultural patterns. Good intentions and a short time horizon for decision making may lead to bad policy that should be continually reviewed for unintended consequences. We've made many pivots to improve agricultural yields in the past. It is time to make another, but other advances are also needed. We should be aware of the rate of change on the planet, whether it is temperature or biodiversity, and manage it so all living things have the ability and time to evolve and adapt. Backup plans include seed banks that keep track of naturally occurring tendencies, crop rotations so soil nutrients are replenished, genetic engineering, and processes like cell culturing. When changes occur so rapidly that plants and pollinators can't keep up, this becomes the only solution until science creates new methods for high yields that are not so destructive in other ways. Reduced population levels and reduced reliance on beef products will lead to less land devoted to crops. In the long run, nature wins. The earth, it will be fine. To manage this risk, we need to always be skeptical, but let the process work. As financial experts, risk managers should interact with others to build solutions as a team. The scenarios we build won't always be perfect, but these efforts will extend our reaction time by being prepared to act.
Max, I've got a couple questions for you. Let's start with this one. How does Ben Franklin's essay from 300 years ago about population align with this discussion about monoculture farming?
Yeah, thanks, Dave. I've written a couple of essays about Malthus and his ideas regarding population growth, and became aware of Franklin's role when I read Malthus's book, an essay on the principle of population and other writings. It's, by the way, as a side comment, it's not an easy read. But in 1751, Franklin wrote an essay, and he called that one Observations Concerning the Increase of Mankind, Peopling of Countries, etc. In it, he spoke of populations geometrically doubling every 25 years in an environment with abundant, cheap land and resources. But more interesting to me were his comments about the role of the economy and family formation, and his assumption that the population would adjust based on available resources. He noted that marriages were delayed when economic growth was slow, and children thus deferred, with the opposite result during good times. Demographic growth depends on expectations. Malthus determined that food production grows linearly and human population grows exponentially. Eventually, there's not enough food, but continually we come up with pivots that make fertilizer plentiful. Monoculture farming was a hyper-efficient pivot that expanded the carrying capacity of the land and output per farmer. This solution traded the risk of famine for the complex and ambiguous risk of ecological collapse. Human ingenuity can temporarily postpone limits, but may create a bigger problem in the future. Today, the world's population is over 8 billion people. Food supplies in the oceans are shrinking, and resources on land are limited, including soil depletion, freshwater scarcity, loss of biodiversity, and climate change. The problem that needs to be solved is now much larger in scope. These factory farms have downsides that we should be proactively addressing, whether growing wheat or raising chickens. Small operations are less efficient, so likely to fall by the wayside, as predicted nearly 300 years ago by Ben Franklin. I see tough times for small farmers going forward. Conceptually, the goal is to balance the cost of a diversified result with a variety of crops, seeds, and fertilizer combinations against the cost of the highest plausible catastrophic failure of a concentrated system. With each historical pivot, we've added complexity to our solutions, making the ecosystem more fragile. Future solutions need to rebuild resilience and ensure stability.
Well, next question, Max. How can natural population balances like war, disease, and famine, how can they be assessed quantitatively?
Well, any natural population regulators that reduce the number of people require discontinuities, something our normal modeling doesn't tend to reflect. It needs to reflect environmental triggers and feedback loops, so a deterministic scenario is required. None of these outcomes is linear, and as with all complex adaptive systems, there's no closed form solutions, only simulations of what ifs tied to resource scarcity. Interactions can be modeled using agent-based modeling, but then this needs to be converted into purely financial assumptions for us to model specific products. A deterministic scenario can follow a narrative or story, such as temperature rise, aquifer depletion, changing the value of cropland, and regional conflicts, slowing population growth and restricting economic growth as money is diverted to those conflicts. One outcome that's especially hard to model, but important to consider qualitatively, is the combination of economic challenges and political change that amplifies into social collapse and political regime change. Whether it's China's Great Leap Forward, COVID-19, Black Death, or World War II, they all generated discontinuities based on high mortality, but also led to regime changes in the areas, in the regions that they impacted. Demographically today, we see Russia as extremely challenged prior to the Ukraine war, and now they're sending many of their young men to fight in a high casualty war and where antimicrobial resistance is expanding and battlefield tactics are creating a kind of a leapfrog evolution of tactics. One way to maintain consistency between reporting entities would be to have a regulatory requirement for specific stress test scenarios. Examples might include climatic tipping points, specific sea level rise levels, or stagflation, allowing the regulator to access results from the same scenario for each firm. The rating agencies could also include mandatory scenarios as part of their process to assess a credit rating. Some situations that would be interesting to brainstorm the resulting scenarios would incorporate drained aquifers, a carbon tax, dead zones from excess nitrates, vertical farms, offshore fish farms, and geoengineering solutions to climate change. These would need to consider higher order consequences of interactions. Externalities should also be incorporated. Resources that were depleted would have to be replaced and paid for. Projects should be tiered so negative higher order effects can be scaled back or the project halted. Dave, do you have any examples that you want to share?
This discussion made me think of was a project that I once did where we were supposed to be modeling a pandemic impact on a life insurance block. And we decided to use a bootstrapping method. And I don't know how many people are familiar with that, but it just means putting the actual historical results year by year, putting each one onto a ping pong ball and putting it into the lottery generator, that spits out a ping pong ball every time. So you're drawing from the actual experience, but in a random order. The experience that we put in the bucket was of the last 100 years, so it included the 1917-18 influenza pandemic, which was great. But the thing that we were modeling there was a percentage change from year to year in the mortality rate. Just a cautionary tale here. The year before the pandemic, the change to the pandemic was, I don't remember what it was, but 10, 20, 30, 50% increase in mortality. And then the year after the pandemic was a similar magnitude decrease in mortality. But in our first pass on this, we treated those as independent events. Well, they're not independent events. They're totally tied to each other. So you have to be careful of things like that when you're doing this kind of modeling. But that bootstrapping was an interesting way of picking up an event because most of these situations we're talking about are most of these rebalancers are going to be event type things that will come about more or less randomly.
On every one of the pandemics that we've talked about, it's not a 1 year event, and so you have correlation between several years even during the event. If you're in the first year of the Spanish flu, the next year is going to be pretty high too, and so is the year after that. It's only when you actually come out of that period, which might last 3 or 4 years, that you have the downward track, and it's correlated too, but in a negative way. So it makes it really hard to model.
Well, it just needs to be done with the regime switching kind of thinking in the model then. Is you have one regime which is the pandemic and the other regime which is not pandemic.
Yeah, I think what most people have done is they just roll all those years into one and assume the whole pandemic happens all at once, which isn't necessarily true, but probably does well enough for a shock scenario to pass muster.
Yeah, that wasn't an option in the case we were talking about. In fact, the reason I was brought in was because of work that I had done showing the S-curve development in a pandemic, which was not something that was in the model that was there before I was brought into the project. Well, let's keep going. I got another question here. In general, Max, what are the differences between addressing a new climate or disease volatility through rapid genetic modification versus the natural genetic diversity that you see from seed banks and traditional breeding?
Yeah, in general, this question requires proactive thinking. Rather than starting from today's environment, think about where you want to be in the future. It's kind of like going to where the puck is going to be, as Wayne Gretzky would say. Genetically modified seeds, or GM, can adapt quickly to a new environment, certainly. So high velocity threats like a new wheat rust variant would follow that path to avoid imminent crop failure. But for long-term food security, the traditional breeding strategy will likely work best with robust, naturally complex defenses going against trending threats like shifts in climate. It avoids having all its eggs in one basket, so to speak, by avoiding a monoculture crop strategy and avoiding the possibility of a single catastrophic failure. You can also combine these strategies in a method that I like. I'm using genetic engineering to accelerate changes that would occur slower under natural circumstances. And you do that by finding specific traits in the seed banks and genetically modifying domestic seeds. So that's a useful method as well.
When assessing monocultural farming risk, what types of experts should be included as stress tests and scenarios are being developed?
Yeah, my opinion is that actuaries and risk managers are natural members of most integrated cross-functional teams. Since we have pretty broad backgrounds and as practitioners work with all the areas with the highest risk exposures, we think about the impact on aggregate risk exposures to the enterprise, risk interactions, both sides of the balance sheet, liquidity, and even capital allocation. For scenarios tied to monoculture farming, I would also include agronomists, ecologists, agricultural economists, and behavioral scientists. Agronomists and ecologists can explain what types of failure can occur and develop estimates of their frequency and severity. Financial experts can then define and quantify losses, financial losses, and develop a hedging program. Behavioral scientists can help to explain how the stakeholders will react to the scenarios. Risk managers bring their specific expertise, but also as an interpreter who is used to communicating with all the other team members. The team can develop an enterprise resilience metric that other risk metrics will align with, determining the ability to survive and maintain core functions after a risk event. The team will start with high-level narrative scenarios that product and asset teams can use to translate into financially actionable terms.
Here are my key takeaways from this conversation. Number one, diversification of crops is key to building resilience, just as diversification of an insurer's risk is key. Number two, it is important to learn to ask the right questions. That's my self-improvement goal for 2026, to get better at thinking of good questions. Number three, the need for proactive adaptability, especially regarding emerging risks. And I told you there would be a quiz about those three terms. Did you pay attention? The quiz is self-graded, so here are the answers. Social fragmentation is the societal divisions that arise from factors such as income inequality, political polarization, and cultural differences. Need to identify social fragmentation as an emerging risk, since it can influence the likelihood and severity of claims, particularly in crisis situations like the riots or social unrest. Continuum analysis is a framework of fluid assessment of risks that allows organizations to navigate the spectrum of stress from normal to extraordinary conditions. And last but not least, drive to thrive. That means targeting thriving in a volatile world instead of just seeking to hunker down to survive. Risk is framed as a potential enabler for growth and success. How did you score? 1, 2, or 3 right? We hope that you have enjoyed this edition of Crossing Thin Ice, and if you did, please like, subscribe, and share with your friends. Thanks. Bye.